Good afternoon, everybody. Today we are going to discuss DC shunt motor. As we explained previously, there are different types of motor. It depends on the connection of the field winding with the armature. So what is shunt motor or DC shunt motor? That's the motor, and we are going to represent the resistance of the armature winding by a resistance called RA, as we did last time, and we have the back EMF that's called EA, and maybe sometimes, to start the motor, we add some variable resistance, call it R start or R series. That's to when we start, maybe we don't want to have the full voltage applied to the motor till it gets to the speed, because as we did in the previous example or previous lecture, that the starting current was like 5 times the normal current. So to reduce it, we may add resistance. Of course, that's not a good way to do it, because there is a power loss in the resistance. There are other ways that you will learn it when you study power electronics, how you can control electronically to reduce the voltage without adding resistance. And that's the supply, the terminal voltage, VT, and the current will be called here IT, terminal current, and the current in the armature will be IA. Where is the field now? The field is connected in parallel to the armature, and most of the time we have a variable resistance rheostat connected to the field winding, so we can control the current in the field, which is going to be called IF. That's the field current. And why we do that? Because when you control the field current, you are controlling the flux, the magnetic flux, and magnetic flux affect the speed and affect the torque. So we like to have something here too. So the resistance of the field itself, we call it the R field winding, and this one we call it R field control, the one that control the field. And all of them, we just add them together and we call it RF, the field resistance. And the current IF and IA, the total or the sum of these current will be IT, the terminal current. So the first thing we observe in the shunt, that IT is equal IA plus IF. That's the first thing, current Kirchhoff law. And we observe that the voltage, the terminal voltage, if you don't have the starting resistance or RSCR, so the voltage of the supply, the same, parallel across the armature is the same, the field. So the field voltage is the same as the armature when you don't have starting. But if we have starting, usually you call this voltage in this terminal here across, this is the armature. You can call this A and A dash. That's, between A and A dash, this is the armature. So the voltage across A dash is called armature voltage, VA. So if you don't have starting resistance, so VT will be equal VA, or VA will be equal VT, the same BF. The BF, it's across the field. So that's why we call it shunt, because they connect in parallel. And as we did last time, we should continue to write the voltage equation of the motor. So we'll have that VA, the armature voltage here, the one in red, is equal to the drop across the resistor RA, which will be equal to RA times IA plus the back EMF EA. That's a very simple circuit. And what else? We have 2 equations, very important equation. We're always using one for the voltage and one for the torque. The one for the voltage, we know it's EA. It has the machine constant. We worked with that before, and we said that Ka is equal to Z, the number of conductor, the number of poles, divided by 2 pi A. And we said it could be equal to P, the number of poles, if the winding of the type of the lab, or equal to 2 if it's wave one. It depends on the type of the winding, the field. And then the EMF EA is proportional to the flux and also to the speed, omega n. And we know that the torque, it's proportional to the flux and the current. And next week, you are going to do experiment for the DC motor, and they are going to measure actually the relationship between the voltage and the speed and the torque and the current. So that's the equations of the DC shunt motor. The thing that distinguishes between other motors, that's IT is equal IA plus IF. And the voltage VA is the same as the voltage of the field. All right. And if you like to find the field current, if you want to find the field current, you just divide the voltage across the armature or VF. You can say that IF here, let me just write in the same equation here. So if you want to find IF is equal, should be VF over RF. And in shunt motor, the VF, the voltage across the field, is the same as across the armature. It's equal VA divided by RF. That's the whole equation you need in shunt motor. If you understand, you could be okay. Let me now move to something important: how you calculate the efficiency of a DC shunt motor. It's very important to understand how to find the loss in the DC shunt motor and how to calculate the power at each stage, because sometimes it's sometimes tricky, but really it's very simple if you pay attention to what's happening. Now, I want you to understand it, not just the question. You look at the DC motor. What is the input for DC motor? What's the input power? Comes from where? VT, exactly, from the source. So you can say that the input is almost VT times IT. That's the input. So we'll say that the input to the DC motor, V input, which is equal to VT IT, is going to the machine. Then, of course, something will be lost, and I will make negative when something lost. So when you look at it like that, to reach the armature voltage VA, so there is copper loss, right? What is the copper loss? In the series resistance RSR, right? And this resistor will be lost. Some circuit they don't have, but here I'm just doing in general. So if you don't have RSR, so the armature power is the same as the input power. But I'm making in general case, so it'll be easy. So I say there is some loss here, and the loss is equal to IT squared times R series, whatever the name of it. So what's left? If you subtract this loss energy from the total input energy, so you will have what's left? VA times IA, because I'm sorry, VA times IT, because the voltage here is VA and the current IT. So now the input to the machine is VA IT, right? The voltage across the whole machine is VA, and the current, the total current, the whole machine IT. So what's left? The power will be VA IT. If you don't have RCS, so VA IT is equal VT IT. All right. So when you go there, so the all power from let me call this point, for example, point X. From point X to beyond that, the all power is going to supply two things. They're going to supply two things in this shunt motor. What they are going to supply? They are going to supply? EF. Not exactly, I mean the armature. You give part to the armature, and the other part go to the field, yes. So the all power will go into the armature, feeding the armature and the field. So now if we subtract the loss in the field, what is the loss in the field? That's the field, right? That's the field. So the field, it means RF total and IF. So we will have loss I square F times RF. That's the loss in the field. So if we subtract the field power from the total power, what's left? The armature power, right? So I will say here, the loss in the field will be I square F RF. So what's left? The armature power. What's the armature power? It's only on the branch AA dash, which is VA times IA, because the volt across A dash is VA times IA. So what's left? VA IA.
What does it say right there? The first like junction that comes off on the where you were just right.
This one or this one?
It's down just a little bit further. Where it says PN equals VTIC, and then it comes in. And
then I square FRF loss. Then what's have VAIA? That's what's left. The power across the armature. This is the power loss. That's the power loss in the field.
The first one.
That's the power loss in the field. And this one, IT square RSR series. So that's the power loss in the starting resistor, or R start, or series resistor. That's used for starting. So if you subtract the power loss in the field, so you have VAIA. That's the power, total power in the armature. And then there is loss here. If you subtract the loss in armature resistance, RAIA square, what's left? The power, the developed power, the one that you wanna take it and convert it to mechanical. That's what I need reach. So let's subtract IA square times RA. IA square RA. So what's left? EA IA, which is called developed power. That's the important thing. Once we reach here, that's, I mean, the power, are you going to use it to convert it to the mechanical energy? Then there is a shaft on the DC motor, and you have the load, and then it starts to rotate with omega. So we're going to have mechanical loss. We call it rotational loss. So if you subtract the rotational loss, call it P rotational, and by the way, you can consider it constant. It does not depend on the load. There is, I mean, little bit dependency, but it can be ignored, not very effective. So what's left here, the power that the load is going to use it, that's the output power. That's the mechanical power. That's the shaft power. Why I mention all these names? Because, I mean, when you read the textbook, you find that the output power name many names, all of them the same. It's the output power. It's mechanical power, it's shaft power, it's a useful power, whatever they say. That's so that will be, so that's important, you know, that you know that's map for how the power is going. That's general. In many cases, you'll find that they don't have RSCR, but you understand, I mean, what I want to get. You want to get in the end the developed power. Yes, you have a question? Yes? Okay. So, very important to know this map because it's general. Sometimes you don't have series resistance in the beginning. Sometimes you don't have R restat of the field, but this is a general case. Okay. So how you find the efficiency? The efficiency, as in any case, any system, it's equal the output power divided by the input power. And output power and the input power is equal the output power plus B loss. If you want to make it percentage, that would be times 100. And if you want to calculate the input power, it's equal to the output power plus B loss. And if you want to find the loss, I'm not going to write the whole question. But you can add I squared, IT squared times RS, I squared. Oh, the whole loss, I mean, just the R on the one on the bottom. You can add all of them. But why I don't want to write it? Because maybe you will not have this R series or R field. And I want you just to put the equation because there's risk in it when you write the equation. I want you to understand, especially some mistakes happen in I square F or F. Because sometimes the power is given across A dash. So it's not included. But if you put the equation and you memorize it, I found that in before that you just make minus I square R. You do subtract it if you have the whole power VA times IT. That's the only thing when you subtract. But if you have VA times IA. So why are going to subtract the field? So that's why I don't want to write. Just let me know. I just want you to understand the math. That's important. Okay. Let's have example here. And the example is in general, not only in efficiency. On can you see it? Is it okay? We'll just read it through it. Let's read the example. The DC machine, 12 kilowatt, 100 volt, 1000 RPM. That's the data of the DC machine. Is connected to a 100 volts DC supply. All right, so we are using the rated voltage, and is operated as a DC shunt. So it's connected as shunt. Because usually they leave the field for you when you get the DC machine. They leave the terminals of the field available for you, and the armature terminals, and then you connect whatever you want. At no load condition, when there's no load, the motor runs at 1000 RPM and the armature takes 6 amp. We don't have load, but there is a current in the armature. You might think if you don't have load, so you shouldn't have current, but you have current. It's small, of course, because why I'm saying it's small? Because when I look at the rated value or the nominal values of this machine, I find that the power is 12 kilowatts and the rated voltage is 100 volts. So I can't tell you what's the rated amp. The rated amp IA rated is equal to the power divided by the voltage, nominal, rated. Let me just make it means nominal here. So the power is 12 kilowatt and the voltage is 100. So what you get? 120 amp. So I know that the machine, if you have load, nominal load, it will take 120 amp, but this one is 6 amp for no load. So why there's current at no load? And this is the armature. The question is, in no load conditions, why there is current? What this current will supply if you don't have load? Usually there is load in the motor when you have load, because it needs power, so it needs current. But no load, but there's current. The field. No, you are saying not the field, it's in the armature. Because you have to have field. If you don't have load, you should have field to build the flux. Yes.
Because of magnetizing force.
Force of what?
Magnetizing force.
No, the magnetizing force is produced by the field, not the armature. So this is, I understand that.
You need it for development.
Developer for what? You don't have load. No, I can hear.
Of the
Back voltage. Because the machine can rotate and you don't have load, right? If you have a blender at home and you apply it in, it's rotate, right? It rotates. But once you start to load the speeds get less. Obviously, there are some kind of flow. If you are you did in the lab the two things, dynamometer in prime mover mode and brake mode, and you found you don't have anything hooked to it or something hooked to it, but you found that like there is a power, there's a torque. This is to supply the loss, the friction loss, the mechanical loss, the rotational loss, because already there is a shaft, there is something, so this needs power, right? So in no load, it's just supply the rotational loss. That's the fixed one. It's rotating. There are bearings, windage, thing like it. But if you have load, so the current starts to increase. So at no load, it's supplying the core and the rotational loss. The rotational loss. Okay. Let's now go to the problem. The first question is, find the value of the resistance of the shunt field current rheostat. you want to cut? Yes.
What did you put next to the P and the B?
What?
What did you put next to
P and the B. Just like the nominal. I want to say that. Let me just write. This is mean when you use this asterisk, just a nominal value. Well, if you don't like it, just let me write something else. Nominal value. N in me is nominal. Or rated. Okay. So now we want to find, the question is to find the shunt field. No, I'm sorry. We want to find the resistance shunt field. Yes. Because as we explain here, I mean, that's the field. You got resistance for the field winding, and you got resistance for the control one in the field, that the rheostat. So how you find RF? In general, if you want to find any resistance, you should find RF in total. You should find RF. How to find RF? You should have two things, right? How to find the total resistance? Any resistance, how you find resistance? Using Ohm's law. No? You should have the voltage across the field and the current in the field. VF and RF and IF. If you divide, you get RF, right? So you need two things, VF and IF. All right. VF is equal VA. That's right. Yes. All right. That's right. And there is information here given in the, we shouldn't ignore the more data. They give you something called magnetizing curve. Magnetizing curve, it gives you the relationship between the current of the field and the EMF produced in the machine. That's what we call as magnetizing curve, and you are going to do it in the lab. It means when you increase the field current, then you'll find that the voltage, the EMF is increasing. Why? Because IF producing flux, and every time you're increasing the field current, you're increasing the flux. Forget about the constant. Constant is there. The Ka machine constant is there, but I'm talking about the variables. When you increase IF flux increase, and when flux increase, then start building the EMF. So that's called magnetizing curve. It's given this data, this one, and to make it simple, it's nonlinear. To make it simple for your calculation, we just said at 1000 RPM, the voltage was which is equal 110.4 times IF, the magnetizing curve. So it's, we make it like linear. We found direction linear, like almost linear. All right. So, and it's giving for you the armature resistance, and giving to you it's given the RFW, the field winding resistance. So if you can find the total resistance of the field RF, and this one is given, then you subtract, you get this one. But first we have to find VF and IF. All right. And as you said that VF is equal VA. So if you find VA, so you have VF. All right. So now let's just look how we are going to do that using the information here. Well, I'm going to use the information that at no load, the speed is given and the current is given. That will help me to find the EA. So we'll say that at no load, the current IA is equal 6 amp, and the speed was given, I think, 1000 RPM, 1000 RPM. And what else? That's what, and I have the equation between the EA. It's given EA is equal to 110.4 times IF. Okay. I'll make sure of the constant I got from the curve, because I rounded for you to make it simple. Oh yeah, that's excellent. Because I mean, let me correct this one. the curve give me 100. I make a linearization, so let me fix this one. That's what I thought, because that's 100. The constant is equal 100.4. All right. When I made linearization at this curve. But if the curve is given, you should use the curve to see the corresponding E for IA. Just I want to make it simple too. Now that's it's given, and I need to find RF, and to find RF, I need VF over IF. That's what I'm looking for, and we know that VF is equal VA. So from this information, let's find how you find EA. EA from the equation that's given here for the shunt, you can find EA. EA is equal to the voltage minus RAIA. All right. So I will write EA is equal to the voltage of the supply minus RAIA. And the voltage of the armature, they didn't mention series resistance or starting resistance. Means that the armature voltage VA is equal to the terminal voltage, which is 100 volt. Then you ask, how do you know it's 100 volt? Because it's given the machine 12 kilowatt, 100 volt. And since nothing is mentioned, meaning they're using the rated value, nominal value. So I'll say the voltage is equal 100. It's the same as the terminal voltage. All right. Minus RA, the resistance RA is given. You give it equal to 0.1 ohm. And IA is given at no load is equal 6. All this at no load, So from that, I can find the EMF. So the EMF unit, it will be equal 99.4 voltage. That's the EA. Why I'm doing that? Because I know VF is equal VA, and VA is 100, but how I can find IF? So I'm doing this to find IF. You ask, how come IA will help you to find IF? Because magnetization curve or magnetizing curve, it gives you the relation between IF and EA. So if I found IA, I can find IF. Yes.
So is VA equal to the terminal voltage only at no load situations?
No, when you don't have series resistance, look back again to the equivalent circuit. That's VA. That's V terminal. What's between them? Series resistance. That's sometimes used for starting.
When that's zero, VA.
Exactly.
Okay.
Yeah, it doesn't depend on load or anything. All right. So now that's why so now I have EA. I can find IF using this relationship or magnetizing curve. So I'll say EA is equal 99.4 equal the constant 100.4 times IF that I don't know. Now I can find IF. IF, I will get it by dividing 99.4 divided by 100.4, and I get IF is equal to 0.99 amp, and that's IF. The problem is solved, the first part, because I have VF, and I know that VF in this case is equal VA, which is equal to 100. And I know IF is equal to 0.99 amp. Now I can find the total RF. RF is the total. RF, we know it's equal RFC plus R winding. In any way, they are equal VF over IF, and VF is equal 100, and IF is equal 0.99. So you get 101 ohm. That's the total resistance of the field. I know the field winding is given, and usually it's given for the machine because I add the resistor. It's external. So RF was given equal to, here's the data, 80 ohm. So that's the winding is equal 80 ohm. So to get RF control, it means the one you connect in series with it, that will be equal 101 ohm minus the field winding, which is equal 80 ohm, and you get the 21 ohm. So that very useful, because it tells you if you want to control the flux in the machine, you can adjust the rheostat that connect to the field to get specific voltage, to get specific speed. So that the first part was easy, how to find that. Okay. Now go for the second part. The second part, find the rotational losses at 1000 RPM. We just talked about it. Rotational loss, how you calculate, practically, if you want to calculate rotational loss in the lab, just connect your machine, DC machine, don't couple the DC machine to anything, and look at the voltmeter. This power, there's no load. This power will be blunt to the rotational loss. Very simple. So you have to look at the problem here, and you see that when you have no load, and this is the speed, you got the amp. So now I want to calculate the power. This would be the power loss, which is equivalent to rotational loss. How you calculate the power in the armature? It's equal EA times IA. EA times IA. Somebody say, why don't multiply VA times IA? Because if you multiply VA times IA, you are including the resistance, armature resistance. That's the loss in the armature resistance. You don't want that. You want the rotational. So you have to subtract this from VAIA till you go to the rotor itself. So the power loss here, that's, I mean, supplying the rotational loss. So that's why. So I will say to the rotational loss, P rotational will be equal EA times IA, not all the time, at no load. EA, we just got it at no load. EA, we got it equal to 99.4 voltage. That's at no load. So 99.4 voltage times current. The current, it was given 6 amp. So when you do that, you get 596.4 watt. That's the rotational loss, and you can consider it constant at any load. All right. Now let's look for the third thing. Find the speed, electromagnetic torque. Find the speed. You want to find N, electromagnetic torque, and efficiency of the motor when rated current flows in the armature. When rated current, the nominal value of the current, which we calculate 120 amp. Okay, and it said consider that the air gap flux remained the same, that at no load, no change of the flux that we got it before. And the second part, it's just when it's affected by armature reactions will be reduced by 5%. I will do for you part I, and you do part 2. The difference between both is just this one will be reduced by 5%, and I'll tell you how you do. Anyway, let me just focus now. I want to find the speed, the torque, the efficiency of the motor when rated current flows in the armature. All right. So IA rated, IA will be equal IA nominal value. Let's call it, since we agree about N, not no load, nominal value. And for no load, we use 0, IA 0 will be the no load, but N nominal or rated value. That we calculate is equal 120 amp. I mean, to remind you, we just divided the power by the voltage. All right. Well, since I'm ignoring armature reaction as mentioned, so it means that the flux at no load, the flux at no load is equal the flux at full load. Let me spell it out. It's better. Full load. That's the requirement in the problem. You mentioned to me that ignore it and make it the same, stay the same. All right. Let's remember that EA at no load, we agree about using this for no load and using this for nominal or rated value. So at no load, we did it 99.4 volts. just in part A. And now I want to find at full load or nominal. How you find it? The equation is VA minus RAIA. That's the equation of finding the EMF. The only thing I'm going now to change the current, because I'm not working no load, I'm working in full nominal, which is 120 amp. So the voltage is still the same. The armature voltage is the same as supply. The battery, you have 100 volts. You don't change it, you have it. So you have 100 volts battery minus RA, it doesn't change, of course, is 0.1 ohm. And the armature current at rated value, 120 amp. And then you get the corresponding EMF when you are operating the machine at nominal values. So you get 88 volt. Expect it to be less because you have load, the speed will drop. Well, so what is the speed? You need to find the speed. Well, the speed, you can say that proportional with the EMF, as we said. Why? Because we said E before. E is equal constant phi n or omega. I'm sorry. So if phi is constant, k is constant, we can say that E is proportional with omega. So I can say E at nominal load divided by E no load is equal speed at nominal load, speed at no load. I can do that, right? Directly proportional. The E at nominal load, I got it equal 88. The EMF at no load, we got it before 99.4. Still, yeah, 99.4. The speed at no load, it was 1000, I believe, 1000 RPM, right? And the speed at nominal load, I don't know it. So that's the known one. So from this equation, I can find the speed of the motor in this case. So I multiply, you have 1000 times 88 divided by 99.4. So it will give you 5.31 revolution per minute. Because I mean, I actually didn't use omega because omega is proportional with n. I used n. I used n because n was given RPM. It doesn't make a difference, no, because you know it's omega is equal to pi. I'm sorry, it's equal pi n over 30. So omega is proportional to n. So you can use it's a ratio. So I got the speed, and you can check your answer. You expect the speed will drop. So if you got something different, it means there's something wrong. The speed drop. It was 1000 RPM at no load. You put the load, the speed drop. All right. That's now I have the speed. I don't want you to lose what we're looking for. We're looking for the speed. That's the first requirement. We got the speed. The second thing, the torque. So how can you find the torque? I told you two important relationships in DC motor, whatever series, shunt, compound, whatever the connection is, one for the voltage and one for the torque. We said that the voltage is equal K constant times phi times n, proportional with the speed. The torque proportional with IA, with the current. That's right, with the armature current. So we know that. But before we do, let's just get omega by making pi n over 30, pi, and n is equal 8 because we'll need it in for the divided by 30. So we get it radian per second, radian per second. We get 92.71 radian per second. That's the omega. That is nothing. How to find the torque? Well, the torque, as we explained before, has an important relation. Torque is equal constant phi IA. Okay. So that's one. Another thing, that's the developed torque we're getting. You ask why you are finding developed torque. You said that in the problem. You got to be careful because I mean, the question can ask you about the thing. Find developed torque, find the shaft torque. If there is any difference, yes. Developed torque, the one, we talk about the raw, I mean, the beginning. The first thing was produced in the machine. Let me show you. It's produced here, the developed torque, before it go out to the load. So you call it developed torque. You call it electromagnetic torque. These two names. And in the problem, they said that find the speed and electromagnetic torque. Here is a shaft torque. What is the difference? The difference is electromagnetic torque is produced. This is the first production of the torque in the motor on the armature. It's not delivered yet to the shaft. This is called electromagnetic. This is, I mean, like something, I mean, born, the newborn torque. This is, I mean, electromagnetic torque or developed torque. Then when it reaches the shaft, some loss will go, rotational loss, bearing, windage, and all this mechanical loss. Then you have the shaft, the torque on the shaft, or the output torque. How can you find? Obviously, since it's the first one produced at the armature, I know there is a relationship between power and torque. Power is equal to torque times omega. So you will say that I also know that the developed torque is equal to the power, developed power divided by omega. The developed power, I know it's EAIA, that's produced in the armature. All right. So now I'm going to use that. That will be EAIA, and EA we got it equal to 88 voltage. Here we have it. That's the EA. And we know that the armature is the nominal value, which is 120 amp. And omega, just we got it for the nominal load, 92.71, equal to 113.9 Newton meter. So that's the electromagnetic torque. I like T developed, or you have to be sure about that, or electromagnetic torque. And sometimes you write it TE only, electromagnetic torque. All right. And then that was the second, you want the speed, electromagnetic torque, and then you want the efficiency. But by the way, I mean, you get torque, you got to be flexible. Torque is also Ka phi Ia, and you can get Ka phi. Why? Because you have E in this relationship, you got E equal to 88. And you know E is equal Ka times phi. So if you divide E by omega, but you got it, you can get K phi. And this K phi, you use the multiply by the current, get the same. You can try it at home. You'll finally get the same thing. All the company chart. All right. To find the efficiency, I got to calculate the power input and the power output. All right. How you calculate the power output? What does it mean power output? Power output means the power on the shaft, the load, the nominal load. How you calculate? Subtract the loss, what loss? The big word. The loss of the no. I mean, because I mean, that's important to understand what you're going to subtract. You got to remember this flow chart is given to you. You want to find the output power here on the shaft. So there are many ways. Which way easy now to get? Yes, from what?
From your power.
What power? Develop power. That's right. Excellent. Because you have here EAIA, develop power. The only loss, rotational loss, and it's given at no load. Subtract, you get the output. You got to know how to do it easy. Because, you know, when you do that, even in real life, I mean, you have to spend, I mean, short time. And the exam, you know, you have to spend no time. So now you go there, you will say, okay, now the output power is equal to the developed power minus rotational loss power. The developed power is equal EAIA EA88, IA is equal 120 amp. Rotational loss was given equal to 5. We calculate this. That's in watt. So you subtract, and then you get the output power 9,963.6 watt. I want to calculate the efficiency. So the efficiency output, input. Second question: how you calculate the input of DC shunt mode? Let me get you the circuit here and there. That's the circuit. What is the input? You don't have, but you remember, you don't have starting resistor. That's 0. So what's the input of this machine? Yeah. VT times IT. Okay, good. VT. What's the value of VT? Somebody else. Okay. VT is equal. Huh? VT equal what? Say it loud. 100. 100. What about the IT? $120. What's 120? I know it's amps. I mean, what current? No, I'm taking what are the currents? What represent? What current represents? Represent armature field total. What current? 2/6. So it's armature. We have been using this IA. It's armature. So to find I total, you got to add armature current and the field current. The armature is 120. So the input is equal V terminal, I terminal. And I terminal is equal IA plus IF. I know that VT is equal 100. I know that IA, it was given 120 amp. IF, I got to get it. I think it was we got it before in the first part. AA 0.99. You're right. Let me. Yes, here you go. IF. So everything is gone. BN is equal 100 times 120 plus 0.99. That would be equal to 12,099 watt. Now it's very easy. Efficiency equal output over input. There are many ways to calculate, but just I'm getting the easiest one. Just the output power we calculate here. We have it 3.6 divided by 12,099 and times 100. Get a percentage 82.35%. That's the efficiency. Usually electric system have, good efficiency. It's much better than mechanical. Mechanical has bigger loss. When you do at home, do the part that including armature reaction, and I'll give you a hint here how we'll do it. If you are going to assume, you say phi full load is not going to be equal the no load, will be equal 0.95 phi of no load. It was given that armature reaction will reduce the voltage by 5%. Okay, I still have 1 minute because there's one last requirement in this problem, and they said that find starting torque if the starting armature current is limited to 150%. If you want to start the machine, so you want to find the starting torque if the starting armature current means you cannot increase the armature current more than 150%. What is the armature current in the nominal value? 120. From that, you're going to calculate the current at the starting, okay? And then how you find the torque? You'll find the torque by multiplying find the constant K phi. That's the easy thing. K phi, you can get it from the part C that we did. And then the current, now we have new current. That's all. The current is 120 times 1.5. That's the new current starting. You multiply the torque. Okay. All right. I will add more solved example because this example took the whole lecture. And next time we're going to do I will put some solved example on how to control the speed of the DC motor, and there'll be a lecture of that. And then we still have DC series motor. That's very important. And then we'll finish that. We'll do the DC generator, which is the same as DC motor, but just we flip it.